All right. So let us continue the course. Just one announcement that is starting from next week, we will follow lectures on Zoom. We do Monday, Wednesday, same time, but on Zoom on my iPad. Okay. But today we follow the course, and tomorrow and Friday we are also going to be here doing the course. Okay. So what did we do? We said that there is a functor that takes us from category of schemes over some algebraically closed field to set of isomorphism classes of families of whatever, families of curves, families of sheaves, families of whatever objects with fixed type. So if you give me a scheme in here, f of s would be the family parameterized by that scheme. Okay, so this is a functor. There is another functor that tells you if you deform s, how the family deforms. And that's called tangent functor, because it's like the tangent in space. So tangent functor takes you from, so this is something that we discussed. So it's defined as follows: tangent functor from some element alpha. Okay, so here we said, let us deform this scheme and see how the family deforms. So we said, I can deform this scheme by extending underlying scheme into some fattening of that thing. So that's a deformation of the scheme. So if I have deformed my scheme this way, and then if I pick an element in the family parameterized by this scheme S, that the tangent functor takes me from OS modules to sets we discussed. And it takes me from n to elements of pi inverse of alpha, where pi is the map from Sn to f of s. All right, so what does the tangent functor do? It's a contravariant functor. If there is a map from S to Sn, the tangent functor gives you a map from f of Sn to fs. So that's basically what the family does. It's a contravariant functor. And then the tangent functor, so you pick some element in here, and it says that it gives you a map from OS modules to pi inverse of alpha. So basically, what is that? It basically tells you your alpha is in here. It's an element of the family parameterized by S. Pi inverse of alpha lives in here. So what is the pi inverse of alpha? Pi inverse of alpha are all those members of the family parameterized by Sn which come from alpha. So it's giving you all the members of the family parameterized by Sn such that after restriction to S, it gives you alpha. So it's the deformation of alpha under extension of S to Sn. That's what the tangent functor does. Okay, so that's what we discussed. So we said that E of f of alpha is the set of isomorphism classes of all elements in f of Sn, whose restriction to S is alpha. S is a scheme. Sn is an nilpotent extension of this scheme. Okay? So example that we made was For instance, if this is the y-axis, if this is the x-axis, the polynomial ring in here is C of x and y, right? Now, if I'm interested in all functions which are supported on the x-axis, but not on the y-axis, I will look at the ideal generated by y, and I kill y, right? So this is what I will do. And this is isomorphic to C of x, right? Okay, so what I can do is I can also take, look at the nilpotent fattening of y. So I like to think of elements which are not only nilpotent fattening of x. I like to look at elements which are supported on maybe fattening of x. Okay. All right. So that's what I will do is I can define by an ideal like this. Something like that. So anything that is supported beyond the fattening of x, I just kill it in here. And this is the ring extension that you have seen before. So I'm sure you have seen this part. So this is the example. So you have a ring, you mod out by this ideal, you get this C. You can take the mod out by the smaller ideal, right? And then the kernel of this thing is the ideal x divided by ideal of x squared. And you always get into a short exact sequence like this. Now this is actually C. This is isomorphic to, well, everything constants are not killed in here, and then C times x is not killed in here because x's are not killed, x squared and above are killed, right? So this is that, and this is exactly C times x. So as you can see, this ring is bigger than this ring. It's this ring plus this ring, okay? This is what we are going to call O of Sn, and this is what we are going to call OS. It's an extension of this O of S by an ideal, which we call N. That's C times x is N. Now, I have this extension like this. If I apply the spectrum functor to this thing, the arrow, the direction of the arrows change. So clearly a spectrum of O of S injects into a spectrum of O of Sn. Spectrum of O of S by definition is S. And a spectrum of O of Sn by definition is Sn. So the scheme S is embedded inside the scheme of Sn, and the structure ring of Sn surjects onto structure ring of S. And the structure rings are sheaves, and they have local module theoretic representation, and this is the module. Okay? So this represents for you a point on the x-axis, because you're killing x, all x's. And this represents for you fattening of that point. Right? Now if you put this in the 2 dimensions, this represents for you, then these will be C of xy. C of xy in 2 dimensions. If you just put one of them, you're killing one of the axes. But if you just put one of them square, you're killing not exactly it, but you're killing anything beyond order 2 of that axis, and so on. Okay? And this is this normal, this is basically another thing which is true. This is the ideal, so we call this I. So this is O of S modulo I. So if you have S and you have some Z in S, subscheme of S such that subscheme of S has an ideal, right? Associated to this is an ideal of Z inside S. Okay, so O of S modulo this ideal is O of Z. That's what it is. It's true, right? Because we know that I of Z in S goes to O of S, goes to O of Z. And this is a short exact sequence. So if I take O of S modulo ideal, I will get O of Z. O of Z. Okay. Then, what about that? So then another thing I can do is I can take O of S and quotient it by something smaller. Ideals have this property that when you look at the product of ideal with itself, it gets smaller rather, right? So O of S modulo I squared. And then here you will have I mod I squared. This is the structure sheaf of something which is very close to Z, but it's not exactly Z. It's the nilpotent fattening of order 2 of Z. Topologically, it's 2 times Z. But algebraically, it's given by functions which are degree 2. It's the difference between x equal to 0 and x squared equal to 0. And what is this thing? This, you know, we have seen it. This is the conormal to Z inside. So if I want to use notation O of 2Z here, O of 2Z goes to O of Z. And this is the conormal of Z inside 2Z. We call it conormal sheaf. And if it is a smooth, it's the conormal bundle. It's like cotangent bundle. Okay? All right, so these are all the things that we have seen before. So here I am, only on the x-axis. What ideal did I kill? Ideal of x minus 0. My ideal is x minus 0. It's ideal of the point 0. So this is O of the point 0, but on the x-axis, O of the point 0 is the skyscraper sheaf, which is one-dimensional vector space isomorphic to C, standing at that very point. So what is this one then? Well, this is also something like that, but it's not exactly the point I'm killing. I'm making it fatter. So this gives me a structure sheaf of the fattening of the point Z, x equal to 0. Any other point I would like to kill in this x-axis, I can give its coordinates x minus a instead of x minus 0. So in 2 variables, I can put these things as x and y. And then I can divide by ideal of the x-axis. Right? Ideal of the x-axis are those functions which vanish on the x-axis. Here is the catch. Ideal of the x-axis are those functions that vanish on the x-axis absolutely everywhere on the x-axis. What could that be? So C of xy, ideal of the x-axis is the things that vanish on the x-axis. Because x-axis is absolutely homogeneously, uniformly given by y equal to 0. So anything that has y in it vanishes on the x-axis. So even though I'm putting y, this is ideal of the other one. Yes, in coordinates has the coordinate ideal, but it's the ideal sheaf of the x-axis. And then y squared gives me fattening of the x-axis. And it also makes sense because if I do this, if I look at this one, and then I will get y mod y squared. If I look at this thing, this is isomorphic to C of x. Well, that's good because the structure sheaf of killing the y-axis gives me all the functions which are supported on x, and all of them have x variable. But this is much more fun. This will be, well, x is not killed at all. plus C of x times y, coordinate y, not ideal, but coordinate. So this thing is seeing x-axis, but a little bit of y-axis. But what is that? It's the flattening of the x-axis in the direction of y. So if I take the spectrum of this thing, which I called S of n, O of S of n, then it's not exactly x-axis, because that sees no y, but it's the flattening of x-axis, so it sees a little bit of y. So, and I will call it 2 times the x-axis. So this is O of 2 times the x-axis, and this is O of x. It's true, only has x in it, and this thing is the conormal to x inside 2 times x. So in algebraic geometry, if you want to deform, idea is your moduli space is given as a functor. If you want to deform a family in here, you should see where the family is getting fed. It's getting fed by a certain scheme. So deform your scheme, rather. And deformation of this scheme is formal, but very rigorous. You know that your scheme has an underlying structure algebra. Structure sheaf. Deform that. That structure sheaf locally is modules like this. All right, so I hope that this confusion about x and y is now much better. Okay, so yeah, it's good sometimes to do this really very concretely in the level of the coordinates and so on. All right. So the tangent functor alpha sees all of those families parameterized by the scheme. So in this example, we had the x-axis. We look at order 2 fattening of the x-axis. If I applied my functor f, let's say for the moduli of stable maps and so on, x-axis, I will get a one-dimensional family of stable maps parameterized by the points in the x-axis. And if I apply it to this 2 times x, or S of n, I will get a family parameterized by this scheme. And then the tangent functor tells me those members of this, which are coming from deformation of x, whose restriction after restricting to x-axis is giving you the original family. Okay, so that's what it is. All right, so we can associate to any moduli functor a deformation obstruction complex. So this is a deformation obstruction complex T of f. I'm going to call it T1 of f, which is the same as T of f, and then T2 of f. T1 of f has this definition up here, and T2 of f is also a functor. For every element after deforming our scheme, for every OS module, T2 of f basically tells me obstruction to those obstructions to existence of elements in f of Sn whose restriction could be alpha. Okay, it's the obstruction space. If T2 of f vanishes, T1 of f gives me deformation space. All right. All right, so T2 of f measures obstruction to having flat deformations of f applied to S under deformation S going inside S of n. And this deformation here is being indexed by n because it depends on what module I put there, right? remember again, I had O of S, I had O of some space modulo by some ideal. That was, I call it O of S. And then here I put some N, and I call this one O of Sn. Now this O of Sn could be O of that ambient space modulo I cubed, or any order. So it really depends on what I'm gonna put in here. All right, but you don't need to necessarily have this kind of description. This is the one that we understand very rigorously. But in fact, any ring extension can be thought of as a deformation. So I don't need to really have this description. I can just call this O of S and extend the ring of O of S by a module and call the thing that comes in the middle the structure algebra of Sn, depending on n. And because it's a structure ring, I can take the spectrum of it. I get an affine scheme defined by this ideal. This is the beauty of algebraic geometry. Anything can give you a space. It's just very, very powerfully general. Okay. So this measures the obstructions to flat deformations, and whose vanishing is necessary and sufficient for the existence of an element, let's call it alpha bar, in f of Sn extending alpha in f of S. All right, so it's not always the case that there are elements in here whose restriction to the original scheme is the original element. There might be obstructions, and T2 of F measures that obstruction. So as soon as I give you an example of T2 of F, you will see that's the case, and we have already seen it because last time we discussed about deformation obstruction complexes or groups. So okay, so let's see one example, one definition. Here's the definition. A tangent obstruction complex is perfect for each alpha and S. Alpha is the member in the family parameterized by S, right? And our notation is still the same. If for each alpha and S, the pair alpha and S, there exists at least locally on S, a two-term complex of locally free sheaves. Locally free sheaves of OS modules E1 to E2 such that for any n Ti of f of alpha acting on n is the ith sheaf cohomology of the induced complex E1 to E2 times n. So, what's the significance of n? It's true that this construction is very general, and n is the module with which you extend the structure ring of the original parameterizing scheme. You have some original parameterizing scheme, like the x-axis. You pick an n, and you extend the x-axis. But we did nice concrete examples. We picked the x-axis. We wanted to end up with twice as much as x-axis. So our ideal, what was exactly ideal of x-axis, modulo ideal of x-axis squared. That was I mod I squared. So this was our choice of n. So this is the n is the ideal of the nilpotent extension of original scheme to here. This is called nilpotent extension because it has finite order. I'm extending this with order 2. X will be 2 times x. X will be 3 times x, so on and so forth. Okay, so n is kind of representing ideal of nilpotent extension of S into S of n. All right, good. Now, this one tells me how families parameterized by S, how families parameterized by Sn can come from deformation of families parameterized by S. But there is this obstruction also. It might be that deforming a family parameterized by S to S of n is not possible, which means it might be that I cannot find an element in f of Sn whose restriction to S is isomorphic to an element in f of S. I might not find such a thing. And if I cannot find existence of such thing, it's because of the obstructions. Now there is, normally as you know, when obstructions vanish, then you can have the deformations. This basically says that there is a two-term complex with cohomologies which are the most important for us. Cohomologies of this two-term complex will tell us about deformation space and obstruction space. So for instance, if you have the moduli space, maybe on the moduli space I can globally everywhere in the moduli space define a two-term complex like that. All right? And then I can ask what happens at a given point of the moduli space. Well, the point is that I can take the cohomologies of these things, as you know, probably from algebraic geometry, or if you don't know it, you just search. Sheaf cohomology, Grothendieck gives you a way of computing cohomology of a complex of sheaves. If you have a complex of sheaves like this, or an object in a derived category, you take the sheaf cohomology, that gives you a sheaf. So for instance, this complex, let's say, sits in degree 0 and 1. Yes? I can take degree 0 cohomology, which basically gives me kernel of this map divided by nothing. And I can take the degree 1 cohomology, which gives me kernel of nothing, which is the whole thing divided by image of this map. So there are two cohomologies. These are sheaves. Cohomology of a complex gives you a sheaf. So the degree 0 cohomology and the degree 1 cohomology of this complex, which is defined globally on the whole space, are sheaves which move around on a space. And then I can ask myself, what is the fiber of these sheaves over every point in this space? The point is that if these two cohomologies are picked up in a way that their fiber over every point of the space, one of them gives you deformation at that point, deformation space at that point. The other one gives you obstruction space at that point. Then this complex is called deformation obstruction complex. So it's a very useful object, okay? It's not just random. If it has that property such that its cohomologies giving us those sheaves fiber-wise over every point of the moduli, this gives me deformation in space, so notion of tangent in space at that point, and obstruction in space, then it's called deformation obstruction complex. Now, if this object in the derived category, this two-term complex, doesn't have any further cohomologies, it's called perfect deformation obstruction complex. You know what is the thing in the derived category? In derived category, everything is realized up to quasi-isomorphism. Do you guys know that? You probably have heard it if you haven't played with it. Quasi-isomorphism means equality in the level of cohomologies. Okay? So in particular, it could be a 23-term complex, which is the same as this one, because in the level of cohomologies, they are the same. The 23-term complex is in a way that only 12 of its cohomologies are non-vanishing, and the other ones are vanishing. And this one, which doesn't have any terms, any tail, matches with it. So when you go to the derived category, you pick these glasses. The glasses are glasses of quasi-isomorphism. You look at, you take off the glass, you see 20-term, 23-term complex, and 2-term complex. You put the glasses, you see them as the same. So in derived category, notion of equality is not exactly isomorphism term by term. It's not that. It's cohomological. It's weak equivalence. This is why perfectness is very important for us. Okay? So we call it perfect. It absolutely doesn't have any further cohomologies. All right? You could have non-perfect deformation obstruction complex. It's fine. It could be a complex that captures cohomologies. Let's say some cohomology, zero cohomology gives you deformation in space. First cohomology gives you obstruction in space. But then other cohomologies also. That's a non-perfect deformation obstruction complex. So this is that. Okay, so there's a tangent obstruction complex example. Let the functor we have been discussing be the moduli functor, parameterizes genus G and pointed the stable maps to X with homology class beta. I'm putting curly notation because this is the moduli functor, and okay, applies to schemes and gives me families. The tangent obstruction complex for this data is given by P1 of m bar gn x beta to T2 of m bar gn x beta, and it's as follows. So it is going to be x1 let me see. Okay, so I have written it wrongly in my notes. Now I will fix it. It is given by Arhan, pull back. So how should I do it? It's a certain Arhan, but we don't know what Arhan is. Do we know what Arhan is? Homomorphism in derived category, right? Okay, but let me not give it as an Arhan. Let me give you what this fiber looks like. So it's fiber over a point in the moduli space, which is a map from curve C with n markings to ambient X. Its fiber looks like the following. X1 also not correct. How should I describe this thing? So, yeah. So let me do it this way. It is given by a complex E1, E2. It's a perfect deformation obstruction complex. And the cohomologies of this E1 and 2, and this is sitting in degree -1 and 0, or 0 and 1, up to a shift doesn't matter, -1 and 0. And it has two cohomologies, is H0, and I'm going to call this complex E dot. Its H0 is given by X1 pull back of omega X to omega 1 of C, twisted by some number of mark points, O of C tensor with N, and it's H minus 1 of E dot, given by X2, the deformations and obstructions. 1 of C twisted by some number of PIs, O of C tensor with N. So I have an S, and I extend it to S of N such that I have O of Sn, O of S, and the kernel module for this ring extension is N. And I have a deformation obstruction complex. There is a complex of two-term complex of vector bundles, which is quasi-isomorphic to it in derived category with only non-vanishing cohomologies. It's not the terms in the complex that give you deformation obstructions, it's the cohomologies. It's a two-term complex, but nevertheless it has also two cohomologies. So it's not E minus 1 and E2, E1 and E2, it's the cohomologies induced by the map from E1 to E2. One cohomology gives you the deformation space at the point, and this is the one that we discussed about last time. X1 between pull back, so where is it? So I'm mapping a pointed curve into ambient X. So if you want to deform this map, you would deform X, you would deform curve, and you would look at the difference. Deform an X is given by the cotangent bundle of X, sheaf of Kähler differential. And then the deformation of this thing is given by cotangent bundle of this thing. But I would like to make sure that the points on the curve are pinned in specific locations. So I would like to remember these things. I take the cotangent bundle of the curve and I twist it by the sum of the curve, sum of the points on it. Now I remember. So this gives you a map. If I pull back omega to here, it gives me a map to omega of C. But because I'm remembering these things, I twist this by the markings. So this is that. And this group we discussed last time captures deformation of a stable map. It's the X group. Everything is pulled back to the curve. And this curve is being parameterized by S. So this is the curve I get over S. And this is the curve I get over S. This is the curve I get over S, over Yes. And this is the obstruction. 1 degree higher gives you the obstruction. If this group vanishes, then under extension of S to Sn with the kernel module n, I can have deformations flatly. E1, E2 is coming from here. A perfect deformation obstruction complex is a two-term complex of vector bundles, such that for any n, TIF alpha of n is going to be cohomologies of that complex. So this is T1 mgn x beta of n. And this is T2 mgn x beta of n. T1 mgn x beta is the cohomologies of this complex, which is a group. And T2 mgn x beta of n is the cohomologies, the other cohomology of this complex, which is also a group. This group is the deformation space, and this group is the obstruction space. Any other questions? And last time, because some of you were not here, we calculated the expected dimension of the moduli space of the stable maps. And the expected dimension is exactly the dimension of x1 minus x2. And we even showed that there is a long exact sequence of cohomologies which actually relates such complicated X group to X between omega and O, or omega of C and O, and so on. You just need to expand it. And then we showed by here's a rim on rock, basically, that dimension of this minus dimension of that is exactly expected dimension we had defined before. Okay? So this one is a step. And this one is also a functor. So this is good, right? Because now you kind of are, this is the part of the mathematics which looks like dark magic. So yes, I mean, there is a space that parameterizes, is underlying this functor, and that's the moduli space. We call it coarse moduli space. It co-represents it, right? Points in this space are realization of this functor at the spectrum of C. That's true. But then there is also a more abstract notion of a space, and that's the stack. And a stack is a functor. So this is the stack. Yes. So this is the stack, and if you remember, Kansevich actually, who's a professor here as well, he proved that this is an algebraic stack, functor itself. After all, the stack is actually a functor. It's a two-functor, fibered over category of topological spaces with group with sections. So, but then when you say a stack, we think of a space. It is, but it's really more complicated than a space. Yeah. Now, it gets even way more complicated when you go to derive the stack. Derive the stack, I think, is the full notion of, much fully decorated notion of a space that you can possibly have. It parameterizes points and their automorphisms and autos of their autos and autos of the autos of the autos. So all the fundamental group, actually, of the space is actually parameterized in the derived step. Okay. All right, so this is the deformation stack, if you like. Yeah, it's correct to say that. I never used it, but I agree with you. So Li and Tian prove that this tangent obstruction complex is perfect. The one for moduli space of stable maps. Okay? And so these are the only two terms that you can pick. Okay. So what else do I want to talk about here? Okay, so given, let me see, do I need to talk about this or not? Okay, yeah, let's just keep it as this. Okay, so you have a perfect two-term deformation obstruction complex. And last time we discussed about construction of the virtual fundamental class space. Roughly speaking, we said that in order to realize the locus of this space, which is of perfect dimension, expected dimension, I need to realize this space, in this case it's our moduli space, as sitting as the zero section of a suitable bundle. So for us, this suitable bundle will be the obstruction bundle together with the section. And this section might not be transversely intersecting with the zero section, which is the moduli space. So our goal is to only look at the zero locus of this section. Why? Because if this is the obstruction bundle, the zero locus of it gives me loci of moduli space for which obstructions are zero. And those are the loci of the moduli space for which deformations are well defined. So if I zoom in, I want to zoom in here a little bit. So let me put a magnifier and I zoom in. So okay, now this is my zoom in. Look at here. This is my moduli space. This is my obstruction bundle. If I look at this particular locus in here, so this is a locus like this. So I pick a point, and this point is my moduli functor, curly M, applied to a ring, a spectrum of C. Spectrum of C. And then I take the spectrum of C, the scheme, the spectrum of C, in particular is, so O of the spectrum of C, the structure algebra of the spectrum of C is C, right? Okay. So I think about short exact sequence of dual numbers, the one I had before. So it is like x modulo x squared goes to C of x modulo x squared goes to C of x modulo x. This was the C, the structural algebra of a spectrum of C. This is that C. So I take that O, which is this C, and I extend it to this. And this is more than C. This is C plus C times X. And this is a little bit extension, square zero extension. So I deform my ring. So I deform my ring and I look at M of 2 times the point, right? 2 times that point, the spectrum of the point. Topologically, it's the fat point of order 2. And now I have deformed it. So I come in here. And the point is that my moduli space, a point in here is a stable curve or a stable map parameterized by that point. And if I deform it, I am expecting to get a second order deformation of the original stable map. Because I am in this locus, I can have such thing, because this is exactly the locus of the moduli space for which the natural section of the obstruction bundle vanishes. But if I am in this locus, I might not get such a map nicely. I might extend my map, and then I look at the image, and the image will be some stable map, but that stable map doesn't restrict to the original one. They don't communicate with each other. So as long as you look at these loci for which the obstruction section of the obstruction bundle vanished, you can have flat deformations. Okay. So constructing an obstruction bundle for the moduli space is needed. And constructing the class, homology class in here, representing not just all of moduli space, but a sublocus of it, on which the obstruction vanishes, is also needed. But this is something we did last time. This is the Euler class of the obstruction bundle, top churn class of obstruction bundle intersected with the class of the base. This is something we did last time. Okay, so now I put this in formal language. The point is that the perfect deformation obstruction complexes are going to be given by two-term complexes of vector bundles. One cohomology gives you deformation sheaf, the other cohomology gives you obstruction sheaf. And your hope is that the obstruction sheaf becomes a bundle. So it's the cohomology of the deformation obstruction complex that gives you that up bundle. Remember, cohomology of a complex on the moduli space gives you a sheaf. Now, if this sheaf is locally free everywhere on the moduli space, it would as well be a bundle. So our hope is that this comes from H1, first sheaf cohomology of E dot dual. That's our hope. Okay, so don't worry about dualization. This is just a convention, a notation, the way we cook it up. So as soon as you have such two-term complex, which captures deformations and obstructions correctly and is perfect, then you can have this picture. All you need to do is compute cohomology, obstruction cohomology of this, and make sure it's a bundle. Then your moduli space sits in it. Take the section of it. Euler class of the section gives you class of these parts. That will be the cutting out for you the locus you want. All right. So let me show you construction of Barrand and Fontecchi of the virtual fundamental class. So I'm going to start from having a two-term complex of vector bundles on my moduli space. Barrand and Fontecchi. Fontecchi. What time do we need to? So we start with 1:15 up until 2:15, 2:45, right? 2:40. Yeah. Yes, or 3. Or 3, yeah. Barrand and Fontecchi, construction of virtual fundamental class. Okay. Since M, I'm going to use straight M. M bar Gn x beta has a tall covering by schemes, then one can work locally over local schemes U. So I'm going to work locally on the moduli space. So given an embedding of schemes U to W such that O of W goes to O of U goes to I of U inside W with the kernel, ideal kernel. The normal cone of U in W is defined by spectrum of summing k from 0 to infinity of I of U in WK, I of U in WK plus 1. Okay. Local scheme. So here's your M. I'm going to cover M locally by affine schemes. Yeah. Yeah, affine schemes. Yeah. I'm going to cover it by local schemes. And then you would ask, what is this W? What am I extending into? No. Yeah. Yeah, it's not necessary. Oh, I see what you mean. No, it's not necessarily a local ring. We are not inverting. So, it's U. And U, this locus U is embedded in a bundle. It's a scheme, right? Bundle is also a topological space. So I would like to find, in some sense, a class representing intersection of this section of the bundle with my base. If the intersection was nice, if this is my base, intersection was transverse, that's obvious. The class of intersection of this is a zero-dimensional class because it's a bunch of points and it would be union of these points. And I can even calculate degree of it. And degree of it will be the number of points, and that would be intersection number between this bundle and my moduli space. So that's nice. But normally this is not the case. I would have some non-transverse intersection like that. So in order to do that, I would like to artificially construct some normal cone to this locus of non-transverse intersection. And then I use the normal cone in some sense to calculate invariance, meaning if I want to calculate intersection of this non-transverse locus, I will construct a normal cone and I intersect normal cone with them. And that hopefully gives me a nice number. So this is exactly what we are trying to do. So I have U embedded inside some scheme. Later it will be part of the bundle. And then I would like to construct formally normal cone to U inside that bundle and then intersect it. So this is that. This is exactly what that is. You know what I mod I square was capturing. Why do you know? Because we just discussed it. C of xy modulo ideal of the x-axis. That's the ideal generated by the parameter y. And then here we had C of xy, y squared, y modulo y squared. spectrum of this thing is x-axis but to second order. Yes. So that's the first order deformation of x-axis in the direction of y. Now, 2, 3, 2, 3. It's basically meaning I start from here, I fatten it again, go 1 degree higher. So that's the second order deformation. 3, 4, 3, 4, and I keep going. So as you can see, the x-axis is being deformed in a vertical direction and a normal to its own direction. Right? By what? How is it being deformed? It's deformed first by y modulo y squared. Then it's deformed by y squared modulo y cubed modulo y to the fourth. So it's being deformed by some ring. Spectrum of that ring exactly, and these are, by the way, we call it conormal, right? These are the conormal. First conormal was a tangent like this, then it's a bigger one, then it's a bigger one. You see the cone. Spectrum of it gives you the affine space, which is normal cone to the x-axis as you keep deforming it, first order, second order, third order. So it gives you this. How beautiful, no? Construction of algebraic geometry. Okay, so that's what it is. Moreover, by Hartshorne or Grothendieck, I don't know. I mean, you can read Hartshorne or you can read EGA. By Hartshorne, the differentiation map induces a morphism. From I to omega 1 of W. So, if I take an element so this is something that we did last time. So we start from space that sits in a vector bundle like that. And the vector bundle has a locus, has a section with a zero locus z. We call this thing z. Okay? Then we can actually see that if I take elements in here and multiply by sections of E, because the sections of E vanish exactly at Z, I get a map from the cone into restriction of E to Z. Right? Because I'm killing those places, I'm killing those functions by places where E is vanishing. So I get a map from the cone into, in some sense, this cone is being constructed over this locus. I can put a strip around this locus. And if this obstruction bundle, E or whatever it is, I call it E, this in here I can call E restricted to Z. Point is that there is, even the picture shows you, normal cone sits inside restriction of E into Z. You can say that. But then also algebra confirms it for you. There is a map from normal cone to restriction of E to Z. And that's multiplication by the section of E. The section of E vanishes on Z. So if you take functions in here and multiply by those, by sections of E, you will get a map from the cone into here because the cone is constructed exactly over the locus where this vanishes. Okay? So this multiplication by those functions over there, that's just a bundle, but this is also true. Differentiation map actually gives you a map from here to here, right? Okay. So if I call this F, this is D of F. Okay. So there is a map by the way, if you are interested in doing moduli theory ever in your life, you should know these are the hardest part. Good news. This is kind of understanding this part essentially makes you capable of doing calculus. Okay? If you really understand the bolts and gears involved, how they are communicating with each other, how they are working to make this machine move, and the deformation theory of moduli theory, you're basically done. It's the hardest part. Okay. Okay. All right. So there's a map. So basically, because there is a map from I to omega, naturally that induces a map from k equal to 0 to infinity of I of k, ik plus 1, to k from 0 to infinity of symmetric k algebra of omega 1 of w modulo omega 1 of w. Okay. All right. So before in that picture I put over that this omega 1 was E. Now I'm just saying whatever, W, whatever. Maybe it's not the obstruction bundle. So this is our W. W is in here and U is in here. You're looking at normal cone of U inside W, and the point is that normal cone sits inside restriction of cotangent bundle of W to that locus. I is the ideal of U sitting inside W. If I take omega 1, if I take I times omega 1, that's the part of omega 1 which vanishes, right? When I take the quotient, what is this thing topologically? This is omega 1 of W restricted to U, right? Everything that vanishes on you, I've killed already. So I get a map from here to here. This is exactly that picture I put. So I put the strip, and this is restriction of omega 1 of W to U. And the normal cone of U in W sits inside it because of algebra. Therefore, spectrum of the above gets mapped to a spectrum of this one. Okay. This one is cotangent space of W restricted to U, as I said. And this is cone of U inside W. Normally, it is shown by this thing, normal cone of U in W. Okay, now there are two spaces, two vector bundles, or I said a space, let's just be grown-ups, two stacks. Two stacks. One is this stack, one is this stack. The difference between a stack, if you really want to, for the working mathematician, the workable things, the practically speaking, difference between a stack and a space is that stack parameterizes all possible automorphisms and higher homology groups associated to the points in the space. That's what the stack does. Stack is capable of not just parameterizing points, but automorphisms of points, because the stack is defined as a functor with groupoid sections. Groupoid means choice of isomorphisms. Two-sided arrows, isomorphism arrows between points in this space, especially point and itself. So that's what the stack is. So it's okay if you call this a stack. There's a stack as vector bundle stack, and there's another stack. There's a map between these two things. Barrett and Fontecchi tell you that if you have a map of stacks, there is a notion of taking quotient of one by the other one. You can define a notion of quotient of this by the thing which gets mapped to it. Think of this as something acting on CUW. I can take the quotient of this by that. Okay, stacky quotient. So let's write that down. There exists a notion of stack quotient due to Barrett and Fontecchi. Okay. Okay. Which one? This is. This one? It's generated by the yes. It's generated by the degree 1 part of it. Yeah. It's generated by the degree 1 part. Yeah. Okay. Because it's generated by I mod I squared. Right? And then I mod I squared times itself. And yeah. All right. So. That's right. So it's just a sheaf at this point. Yeah. It's no. Don't need it. For now, it's a formal construction. You don't need. Why do you need local freeness? For now, you don't need it. I said there is a notion of vector bundle stack. Yeah, but you don't need it. Think of it as a stack mapping to another stack. There's a notion of a stack quotient. Yes. Yeah. Let me see. Do we need that? Let me see. Do I need this to be local? Definitely, what I'm putting in here needs to be locally free. It needs to be a bundle. Okay, that needs to be a bundle for sure. What could go wrong? Yeah, let us not for now assume that it is locally free after resolution, after restriction. Okay, ambient space needs to be locally free. Yeah, ambient sheaf needs to be a bundle. For now, we assume that it's a bundle. Okay. So there exists the notion of this. So the Parent and Fantecchi define stacky quotient of C U and W by TW restricted to U and call it intrinsic normal cone. The reason they do that is because, and the reason they call it intrinsic normal cone is that they like their construction to be independent of the choice of ambient space. All right? So in some sense, they eliminate that choice by taking the static quotient. This is as rough as I can put it. All right? So here are some facts. Intrinsic normal cone, is independent of choice of W, which implies that if we pick an atoll covering M union of UI, this is not the curly M, but this is like M, then the induced locally constructed intrinsic normal cones glue to each other. To give the intrinsic normal cone of M. Okay, so somehow, as I mentioned, this obstruction bundle is going to exist over the whole moduli space. And over different loci, you will construct these local cones, normal cones. And then you would like to intersect those with the base. The construction is local. So locally you look at U, and locally you find some W U embeds into. And you look at local normal cone of U inside W. This technology of taking the stack quotient, modding it out by this restriction of W to du, and allows you to basically get rid of the choice of W. So essentially, these normal cones will be equivalent to each other via gluings. Yes, that's right. Yep. That's correct. Okay, so these glue. And here is the remark. Note that the sum, okay, from 0 to infinity of ik plus 1 is generated. This is what you asked. Is generated by I1 modulo I squared by the degree 1 part. In particular, there is a surjection In particular, there is a surjection from k0 to infinity symmetric K algebra of I mod I squared to k0 to infinity of ik plus 1. Yes. Therefore, the spectrum of this thing is a surjection, and the spectrum of this thing embeds inside the spectrum of this thing. But now this is kind of really interesting, because what is this? This is the conormal sheaf of U inside W's. So it's actually telling you that conormal cone sits inside conormal sheaf globally on the whole moduli space. And if you make this choice of W independent, then intrinsic normal cone of the moduli space sits inside intrinsic normal sheaf of the moduli. Okay? That's what it is. Now, we know that M is not necessarily smooth. And smooth. In particular, it is governed by its singularities, are governed by its cotangent complex. This is the illusies. This is due to illusi, look illusi, former syntagmatic. Yes. So if you have a space which is a smooth, then its tangent sheaf would be a bundle and its cotangent sheaf would be a bundle, right? So then we have no issue with omega of M. This would be a bundle. But if it is not a smooth, then you can embed it inside some ambient smooth space. And embedding in the ambient smooth space allows you to capture how far is M from being smooth, to compare it. So in particular, if the ambient smooth space has a cotangent bundle, the cotangent sheaves in here will see for sure via this embedding, you can have a term which is restriction of cotangent bundle of A to M. But restriction of this to M will not keep it as a bundle. Answers your question, it's not. Because M is not necessarily smooth. And if it is not smooth, then this thing will not remain as a bundle. So it has a term that comes next to it. And then if this embedding has an ideal, if M is embedded inside A with the ideal of M inside A, the first thing that you will see in here is the ideal of M inside A modulo I squared. So it's the conormal sheaf of M in A. And then you will have all the other terms. I square mod I cube mod, and all of them. And this complex might just go for infinity. So the cotangent complex that Illusi defined is actually can be an infinitely many term complex. And every space has it. If the space is a smooth, its cotangent complex will be just the degree zero part, which is just a cotangent sheaf, which is a bundle. But if it's not, it keeps going. Right? So this is what the cotangent complex is. And we are going to use it. So we know that M is not necessarily smooth, so it has a cotangent complex. Let's call it L dot. Normally it is used by this notation, where H0, first zero cohomology of L dot of M, gives the deformation space of M at each point. Again, when you have a complex, taking cohomology from complex gives you a sheaf. It's a sheaf cohomology. This sheaf roams around on the space, and if you look at fiber of this sheaf over every point of the space, the zero cohomology sheaf gives you deformation space. This is what the cotangent complex is exactly. All right? And H minus 1 of L dot of M gives the obstructions. Obstructions at each point. At each point of M. Okay? The problem with working with cotangent complex is that there are obstructions to obstructions. H minus 2 gives you a shift that gives you obstructions to obstructions, and H minus 3 and H minus 4. This complex is non-perfect complex. It is a deformation obstruction complex, but it's not perfect. Obstructions to obstructions. Okay. And it goes negative. So first one is omega of A restricted to M. Then it is I mod I square, and it keeps going. This is in degree 0, this is in degree minus 1, it keeps going back. You see? Deformations. This is almost deformations. And in this level, obstructions, obstructions to obstructions, and so on. We don't like that. We don't like to work with the cotangent complex. Remember, we have, let me summarize class of today. We have tangent deformation functor, tangent deformation complex. If it is perfect, then its cohomologies gives us deformation in space and obstruction in space. And it's obstruction and nothing more. So as I go around and I glue obstruction spaces, I can think of these obstruction spaces as fibers of certain H minus 1 or H1 cohomology of the tangent deformation complex. And these give me a bundle. This would be the obstruction bundle. And then I can see that my moduli space sits as the zero section of the obstruction bundle. And I have a section of it, and I can look at the zero locus. I can define the virtual cycle depth. This doesn't give me that. This does give me an obstruction sheaf. It's a complex. It's H minus 1 gives me obstruction sheaf of the moduli space. But that's not nice, because it's a sheaf. My moduli space sits inside this sheaf like this. The sheaf jumps in dimensions. I don't like that. I cannot work with this thing. Some section of it in here, some places vanishing. I don't like that. I would like to produce a bundle. So I would like an obstruction bundle, which probably is close to this, but bigger than this. What makes this not being a bundle is certain other sheaf in here. Maybe I can put all of these things in here. Now you see, if I can put the whole tail of this complex in here, it would be nice, right? Kind of, I get something much bigger, but then I can guarantee that there's nothing behind it. So I need to make it big enough so that it's guaranteed that it's a bundle. So no more cohomologies. So the whole business in this technology is actually replace cotangent complex with something else that models the cotangent complex almost like approximately, in the sense that its zero cohomology exactly gives me deformations, and its minus one cohomology give me an obstruction which is a bit bigger, and that obstruction is guaranteed to be a bundle, and no more obstruction. So when you have no more obstruction, it means that this thing is going to be a bundle, right? Because the thing that comes in the kernel of these maps, when they vanish, this can be a bundle. So if I can guarantee that nothing is in the kernel, then this would be a bundle, right? So I'm going to hook up a replacement for L dot of M. That's the better choice. And then I use that replacement, take the cohomologies, take the obstruction bundle that it gives me, and then realize I'm sitting inside it. Normal cone inside that, and the whole business. Okay? This is basically what we are doing. Okay. So let me see. We are already 2:45. Maybe I can say one sentence. Yeah. Cotangent complex. No. It's the work of Parent and Fontaine. Yes. Use it, yeah. They use it because this is what matters. This is the one that gives us the structure of the moduli space. But we don't need all the higher obstructions. I just need first order obstruction. So I construct some complex, which is the shadow of this, but with nicer properties. That complex, because it approximates L dot of M, is going to be another complex, so I'm going to call it E dot. And E dot is not M, but close to M. So E dot has a map to M, rather. And I'm going to call it deformation obstruction theory if it's capturing deformations of this. So in the level of H0, there must be the same, but in the level of H minus 1 of this one should be bigger than this one, because this one I want to be a bundle, this is a sheaf. Okay? So that's exactly what I'm going to put in here and end the class today. So, okay. Gives the obstruction space, the deformation obstruction theory of M then is given by a map, is given by a complex E dot in bounded derived category of M together with the morphism L dot to E dot. I'm going to call this morphism phi, such that H0 of phi is an isomorphism, and H minus 1 of phi is a surjection. For some E dot in bounded derived category. I think this is a good place to stop. H0 captures deformation space in here, and it needs to, if it is an isomorphism, it guarantees that this complex behaves very similar to cotangent complex, so it's also deformations. And H minus 1 of L dot is the obstructions, but if this map is a surjection, it means that this one hopefully will give us a bundle, but this one is not. E dot of M is called to be perfect deformation obstruction complex if Hi of E dot of M is equal to 0 for all I not equal to 0 and minus 1. So we are going to look for a map from a suitable complex to L dot of it that doesn't have any higher cohomologies. If we have that, then this produces for us a much bigger bundle, obstruction bundle, in which M sits nicely, and then the section of this bundle intersects M, and that intersection gives us an invariant for it. Now you might say, this invariant depends on E dot then? It does. So you can have a space and you can have several nice candidates for an obstruction complex to this space, meaning as long as you can find E dots that satisfy this condition, all of them are allowed, and the invariants they produce might be different from one another. It's the bounded derived category of coherent sheaves on M bar, because this is a complex of sheaves and this is a complex of sheaves on M. It's true that M bar itself is a moduli space of stable maps. But these are sheaves defined over all of M bar, and these are complexes defined over all of M bar as a space. So it is actually sitting bounded derived category of M bar. Points of M bar are maps, curves. Correct. Okay, great. So let's continue. So at least so far I told you that we are going to be here, and then from here, assuming that we have such a thing, I will construct a virtual cycle for you next time. Oh yeah, it's complex. Thank you. So tomorrow and the day after tomorrow we will be here. So tomorrow morning and then the day after at 1 p.m.